All right, folks, welcome back to the third Tuesday of the spring 2021 semester. We're here again with the MathMinds project. Most of you know what we do here, but if there's anybody who is new that I didn't pick up on the list, essentially what we're doing is providing free open math training geared towards business math for predominantly, we've been doing it for students at Brooklyn College, but we've since opened it up to students across CUNY, specifically making a big effort to get Baruch students in. Are there any Baruch students on the call today? Raise your hand if you're from Baruch. Just give it a little hand raise. See if anybody joined today. I don't think so. Okay, not yet. We'll get Baruch folks on here soon enough, I'm sure. We're speaking to Baruch administration about helping us spread the work amongst Baruch College. But of course, Brooklyn College is near and dear to my heart. Been affiliated with Brooklyn College for a couple of years now out of the business management department, and happy to be exactly there. All right, so today we are featuring a new math mission. And as you know, the format of the meetings here are not like a typical, it's not a math course, right? So we're not teaching you theory by theory. What we're aiming to do is bring you real life applications that you will run into, if you haven't already, that you are sure to run into at different times in your life based on our experience. This is the exercises here and all our math missions are extremely pertinent to your day-to-day life and activities. Of course, it helps you in school as well. If you're taking any courses that involve math, it only helps to build your mathematical thinking. All right. So if you, and again, if you missed our first meeting or the last meeting, we do have recordings. We have a channel, a playlist, I should say, under the Brooklyn No Brainer YouTube channel. So Michelle, if you can just post a link to the Brooklyn No Brainer YouTube channel, and in there you'll find a playlist, and every week we'll be adding these recordings to that playlist. So you can watch previous ones if you want, even though you're here today. If you don't understand something, go back, watch the recording later, and go over the exercises once again, because we will move quickly here. Okay, so before jumping into the questions today, the math mission, I should say, are there any questions on your side? Anybody want to share anything or have a question they want to ask? Let me actually have a look at the poll. So I'll end the poll here and share the results with you. So 3 of you found the mission really tough. 2 thought it was tricky but doable. 1 knocked it out of the park, and a couple of you didn't get to it. That's okay. I'm glad you're here anyway. Perfect. That's the perfect distribution I'd like to see. I want to see it challenging you, but not so much that it's not going to be effective when we go over things. So I'm glad to see that distribution. So let's jump in. And again, we're counting on you guys to help explain your solution method to the group. Of course, you have myself and our math mentors here to back you up, but we are encouraging everyone to jump in and provide their point of view, their explanation, because a lot of this is really about learning to think more mathematically, and a lot of that comes from hearing other people and their points of view. So today's mission, or this week's mission, was called Let's Take a Hike. Are you guys into hiking? Raise your hand. Give me a little hand shout out with a hand up if you're into hiking at all. I personally love hiking and thought that would be fun, just to think about how to create math exercises around going on a hike, which one might not think like, what does that have to do with math, right? But hopefully if you've gone through this, you see how that can come into play. So in this hike, there's you and 3 friends, and you're about to do this hike, and you're faced with some questions, some challenges before you get started. So let's jump into the math mission. The first challenge was, and for those of you, you all live in New York, right? Is one of the big things about New York is we have too many choices, right? If y'all, can you relate to that? Too many restaurants, too many bars, just it makes it almost difficult to make a decision, right? So sometimes we use math to kind of help us make numerical, empirical decisions, right? So here's an example of how you might do that for choosing between 4 different hikes that you're considering, right? So I'll just read the question out loud and then we'll give someone a shot to provide their answer. Between you and your 3 friends, you must first decide which hike to do. You're choosing between 4 awesome Hudson Valley hikes based on 2 criteria. 1, the number of times each of you did that hike in the past, and 2, the hike's distance from New York. Now here's the important part. You want to choose a hike location that you guys have collectively visited the least and is also relatively close to New York. So you want to somehow get both of those criterias in, right? To do that, you'll rank each of these 2 criteria, 1 through 4, calculate the average rank, and choose the hike with the best average rank result. With 4 individuals to consider and 4 different hikes to rank, think of a practical way to get that accomplished. Which hike do you choose and why? Here's the data. You've got columns for each of the 4 hikes, and your rows are, the first 4 rows are the number of times each of you visited those hikes, and the last row is that hike's distance from New York City. Who wants to jump in here and kind of share their thought process? Who wants to jump in?
My name is Danish.
Danish, nice to talk with you. Danish, aren't you from Baruch?
Yeah, I'm from Baruch.
Okay, so you must have jumped on after I asked the question, who's here from Baruch? Welcome to the MathMinds project. So go ahead, Danish.
So from just looking at all the numbers, I would assume hike A because so friend 1, 2, and 3 all went to it 2 times, and I went to it once. So it wouldn't going again would only make it 3 times for each of the friends. So it would be a good experience, and it's only 75 miles. I think that's reasonable. I don't think 200 plus miles or 150 miles. It's good.
Okay.
Because it's
So
sorry,
go ahead.
one more thing, because I think this is our first time hiking together, so I think we should go to a reasonable mile. 75 miles is good. Going past that would be like too much because we're going our first time.
Well, sure, but the exercise also did specify that, right? So relatively close to New York. So you're right to choose something on the lower end, but then you had to figure out how to blend this information in with this information. So you kind of looked at it and said, well, it looks like hike A, people didn't go on it too often, right? That's kind of what you said. But Danesh, can you give me like a way to think about it mathematically? Like, how could you prove to me that hike A from the perspective of times visited, how can you kind of show me a number that helps the group understand why hike A is best over B, C, and D? What do you think?
Um, Let me see. No,
Because
I'm
for
not
each,
sure.
okay, if for each hike, there's 4 pieces of data with respect to times visited, right? So we want to find a way to blend that together in a nice, practical, easy way. Can someone help Dinesh with an idea?
Unless I'm incorrect, if you add up all the hikes you did together on hike A, uh, you get a 7, and then divide that by 4, you get 1.75, indicating that all combined you've hiked at an average of about 1.75 times, which is fairly
Yes.
low, and then it's still an extremely uh, low distance away. A hike
Excellent.
B, they hiked about 1.25 times, which is less, but uh, I mean, 200 miles away kind of makes up for, you know,
Okay, let's go with that. Who's this talking, by the way?
Elliot.
Elliot. Okay, thanks. So what Elliot did, what is this metric called, Elliot? What did you actually do here? What is that called?
I found the average amount of
Average.
times they hiked together at the one.
Exactly. So Elliot said, hey, you know what? There's 4 people. We know we want to get a collective metric. So the nice, simple collective metric is to take the mean average, which is exactly what Elliot did. And then he did it also for hike B. And you get actually a lower average, right?
Yes, you get 1.25.
So just by going off of not the
That's
distance data, but from the visits data, hike B is better. And now hike C and D, did you get averages for those?
Yeah, hike C is 3 and hike D is 4.
All right. So now what do we do next, Elliot, with that? What are you thinking?
Well, I mean, you know the averages of all of them now, and since it asked it to go to a place where they want to, you know, go the least amount of times, you could probably, I guess, cancel out C and D because they've each gone there an average of about 3-4 times. It's fairly high. And then A and B are your 2 options, and to keep something relatively close to New York City, 75 miles is the closest. So I guess that would be the hike they choose.
Okay. So A is the right answer here, but I'd like you to go one step further here and kind of empirically, like rather than just kind of at the end there, you're kind of you're just kind of looking at it and thinking hike A makes sense. But what if we want an empirical metric, like we want a metric to prove that hike A is the best hike? What could we do? Obviously, the distance data is different from the number of visits data. So how can we bring those together? Any idea? All right. Anybody want to help Elliot with an idea? Oh, yes. Actually, good point in the chat box. This is 5/4, not 5/3. Thank you. So we're right there, guys, right? So what if I were to create this little table? Sorry, you know what? I'll just try to work this out on the PowerPoint slide. What if we were to rank both of these metrics, rank the averages and then rank the distance, right? So we know the ranked averages, right? The ranked averages for frequency visited, right? B was the number 1 rank. A was the number 2 rank. C, I believe, is the number 3 rank. And D is the number 4 rank. Now, why don't we then rank the distance of each hike?
You can, I think you could add them all up, and then find the average mean of the distance, the total distances. If you
Well,
combine,
now let's think about that. We could do that, but how is that going to help us if we had the
the average
average?
would be about 145.5 miles away, and I guess you could base that off of the rest of the hikes are above the average distance, whereas hike A would be below the average distance.
Oh, I see. Interesting. So you could look at it that way. So you could say, hey, let's take the average and then let's look at what's above the average and what's below the average. That's fair. That's fair. But there's actually something we can do to get even a little bit more specific than that. Rongling is going with standard deviation. So Rongling, can you speak up on the audio?
Because for me, it seems like you're calculating the standard deviation for somehow.
Of what?
The frequency and the distance.
Okay, so can you explain to the group like what standard, just very simply, nothing math, nothing, no formulas, just what does standard deviation tell us, Rongling?
Like I think is 95% of the ranges of like most parts?
I think you're kind of thinking about a normal distribution and kind of standard deviation. You're close, but even more simply than that, what does standard deviation actually give us? Think of the word deviate. What does deviate mean to you? I'll give you a hint, okay, or I'll help you out here. So if you want to think about this is for everybody, standard deviation tells us the spread of data, essentially, right? So when there's a big standard deviation, the data has a more spread. It's more spread out. The differences between the highs and the lows are bigger. And if the standard deviation is lower, then the deviations between the highs and the lows of a data set are tighter, okay? You could work in standard deviation here, but that's kind of overcomplicating things. Here, I'm going to circle a word on the slide, rank. Rank. Why don't we just rank the distances? Now, there was the idea to average the distances and then look at what's below and what's above the average. That's not bad. That's a good idea. But we can also rank the distances, right? So the shortest distance is A, so we'll rank that 1. The next shortest distance is D, so we'll rank that 2. And then hike B is 3. And hike C is 4. And what could we do from that? Well, we could just simply now, this is a very practical solution. There's nothing extremely scientific going on here, okay? But we could simply say, okay, you know what? Let's take the average rank. Let's see what that gives us. So we've ranked these two characteristics, and now let's average them. So here, the average between 2 and 1 is 1.5. The average rank of B is 2, C 3.5, and D, the average is 3. So when we average the two ranks, and then we essentially rank that, right? We rank this row right here, this set of data, you can see hike A, the first one here, has the lowest average rank, 1.5. Now, going all the way back, the first person who, and I can't remember right now who spoke first, but the first person on the call had the intuition that it was hike A, okay? But now we used ranks and mean average to help us empirically show why hike A is the best hike, okay? So I hope that makes sense. Any questions on that? If not, we'll move on to challenge number 2. And there's the answer. Again, choose hike A, has the best average rank. Now, can I get one of the math mentors to volunteer to kind of introduce this exercise and kind of walk the group through? Anybody want to, either Lin King or Eliana, one of you guys want to jump in? Do we have a volunteer? All right, while you guys are considering, let's look at challenge 2. And now we know we're doing hike A, it's 75 miles away, right? We know that. You now know how far you're going to travel, 75 miles, right? But you have 3 choices to get there. You can ride your bikes, it's pretty far, but you could travel by car or take the bus. If you travel by bike, you expect to ride an average of 15 miles an hour. If you take the bus would travel an average of 40 miles an hour. And if you go by car, the car will travel at an average of 55 miles an hour. So part A, if you and your friends chose to ride your bikes, how long would it take you to travel to the starting point? Can we get a volunteer to give an answer or provide an explanation?
I have an answer.
Okay, who's this?
Wrongly.
Wrong Ling. Okay, what do you have?
I have 5 hours for riding the bike.
Okay, and that is the correct answer. Do you want to just tell us the math there?
Yeah, because we're using the 75 miles from the path A, and then you divide it by the average 15 miles per hour.
So 75 is our distance,
Yeah,
and you're dividing it by,
15 the miles, 15 miles per hour.
which is the rate, right? And
And-
folks, for everybody's edification, we're using this basic form, this model, where distance equals rate times time. So we can also just rearrange that to distance over rate equals time, which is what Rong Ling just did here. And she got 5 hours. All right, Rong Ling, how about part B? If you specifically compare the bus and the car options, how many travel minutes can you save by traveling there by car rather than by bus?
Okay, for this one, I did a calculation, but I'm not sure if it is right, because I got the 30-minute for the 30-minute for the answer.
Yes, it is correct. So you can explain how you got it.
Okay. I'm still using the 75, but divided by the average of 40 hours per hour and the 55 miles per hour.
So for everybody, 75 over 40 is the distance divided by the rate of the bus. And the 75 over 55, oops, is the distance over the rate of the car. So the time for the bus is how many minutes or how many hours? First, you're gonna get a hour, the answer in hours, and you have to convert, right?
Yeah. I get the number will be 1.875.
So 1.875 hours.
Wait, no. I converted into the 1.75 is 75 divided by 40, and then that's not the hour. I convert the hour into 1 hour 50 minutes.
Well, you know, this 1.875 is technically hours in decimal form, but then you need to convert this decimal into minutes, right?
Yeah, I convert the decimal into 50 minutes.
Right. So how you want to, can you explain? Well, I'll just help you here. So if we want to convert that into minutes, we can multiply that decimal part by 60 because we know there's 60 minutes in an hour. And then that answer is what is your answer? 50 minutes?
50 minutes.
50, right? So the bus is traveling 1 hour, 50 minutes. And how about the car?
Car, I did 1.363.
And what is that in terms of hours and minutes?
I think it's 1 hour 20 minutes.
1 hour, 20 minutes. And the difference is, as Rong Ling said, 30 minutes, which is, now I got 30.7 minutes, but 30 minutes is good, right? I think that's just a matter of how you round off earlier in the exercise. So 30 minutes is good. Does that make sense, guys? This is how we might use rate or in a real life situation, right? So if we wanted to kind of figure out how much time we'll save by taking one mode of transportation over another one, sometimes we actually find ourselves having to do calculations like this, right? And that can be valuable, right? So if, for example, if you only have limited time to get to the hike, do the hike and come home, you'd want to know how much longer is it going to take you to get there by one mode of transportation over another one. Okay, so nice job, Runway. Nice job. Let's move on to challenge 3. If you guys have a question, feel free to throw it in the chat box. Otherwise, we're going to plow forward here. Now, this one was a little bit of a tricky challenge. Try to give you guys some hints. Why don't you all read this exercise again to yourself? I don't need to read it out loud. Just read the text, and I'll give you a minute. And if you want to try it, we'll just give you a minute here to kind of get it started, and then I'll jump in. Okay, take a minute here. All right, folks, you should have read it, at least read the exercise by now. We're trying to essentially find the distance of the hike, which is basically the distance of the blue line. The problem is all we have is the end-to-end distance. This black dash line is 8 miles, but the 8 miles doesn't account for the fact that we actually have hills to walk up and down, right? So provided you with some angle measurements, that should be a little tip off that we might use geometry to actually solve this exercise, right? And the key is, we know that the black end to end is 8. What is, the key is to figure out what, these hills, how much more does that add to the hike distance? So obviously the hike is greater than 8 miles. The question is how much greater? Lin King, you want to try to explain this one?
Yes.
Okay, so you go ahead and explain, and I can draw on the. Oh, you can draw on the slide
Yeah,
yourself.
I
Actually.
got you.
Okay.
Yeah. So what I do is calculate this one and this one out. Figure out like how much is on the bottom. So because this one is 30 degree, so this angle, this triangle, 30-degree opposite one is the half of the
Hypotenuse.
hypothesis, and then this one should be 1 here. So 2 divided by 2 is 1. So the bottom half of the bottom here is square root of 2 square minus 1 square is equal to square root of 3. So the whole bottom is 2 the whole bottom here is 2 square root of 3.
Now
And
let's
then
actually just stop for a second, because those of us who have not done geometry in a while will be like, kind of like, what is she doing here, right? So Lin King recognized that we have two 30, 60, 90 right triangles, and we know those are special right triangles in geometry. So the sides have a very specific ratio, and they're like what you see here. She knew that the hypotenuse given was 2, which makes it very easy to solve for the other 2 sides. And then she recognized there's 2 of these triangles, and then so she easily calculated the distance from the distance of the black dash mark from one end of the mountain to the other end of the mountain. Okay, go ahead. Sorry, Lincoln.
Yes, it's okay. So for the second triangle here, this triangle here, because 3 of the angles are 60 degrees, and the sides are the same, so they are also 1.5 millimeter here.
And that's an equilateral triangle.
Yes. So we can know, like, except those 2 we can know, like, A together, and then change the color. So I will use 8 minus this 2 part, 2 square root of 3, and then minus 1.5, and then plus those 2 here together. So it's 2 times 2 plus 1.5 times 2.
So Lincoln, there's a question in the chat box, which is
Yes.
how do we know this is 1, this height?
Because there's 30 degree. The side is like corresponding to the 30 degree is the half of the hypothesis.
Hypotenuse,
Yeah, hypotenuse.
right? So
That
it's just,
is like, that is what I remember, like when
yeah,
I learning geometry. There is principle saying that, like, if the one of the angle is 30 degree, the side is opposite to it is the half of the hypotenuse.
so that and that's correct. That is you have to know that to solve this exercise, you have to know those relationships here. So if let me just go to the whiteboard, since this might be something that people haven't seen in a while. I'm going to just do a new share. Right, so if we have a right triangle, right, this means this is 90 degrees, right? This is a right angle. This is a right triangle. The sides are always in this proportion. Okay, always. Now, so that means that if I have a triangle, these are ratios though. So if I have a triangle and let's say, for example, the hypotenuse is 10, then we know that the side opposite 30 is half of 10. In this case, it will be 5, okay? And this side would be 5 root 3. Okay, so these are essentially the ratios. The sides are in that ratio form. And the key is just to know which side is opposite 30, which side is opposite 60. The side opposite 30 is always the smallest value, right? Remember it that way. The smallest value is half the hypotenuse. And then the side opposite 60 is in between, right? 1.3, root 3 is about 1.7 or so, right? So it's in between 1 and 2 in this case. And if we had, like I said before, if we have hypotenuse of 10, then small side would be half of that, or 5. And the third side would be in between 5 and 10. In this case, it would be 5 times root 3, which is, I don't have my calculator next to me, but it's something like, about 7 or 8, between 7 and 8, in that range. Okay. Has some questions in the chat box, maybe? All right, so I see some responses. Great. I'll give you one more since we're on the topic of reviewing geometry. Probably never thought you would do geometry, but hey, you never know. So the other special right triangle is a 45, 45, 90. Okay, so in that case, the ratio of the sides is 1, 1, root 2. Obviously, if you have a 45, 45, 90, these two legs are always the same, right? So essentially, the hypotenuse is whatever the leg is times root 2. So for example, if I have an exercise and the legs are 7 centimeters, the hypotenuse is 7 root 2 centimeters. Okay. If I have 100 inches, 100 inches, hypotenuse is 100 times root 2 inches. Okay. So these are always, the sides are always in this ratio. And then the exercise, we talked about equilateral triangles. Equilateral triangles, where the angle degrees are 60, 60, 60, right? The sides are always the same. That's why in that exercise, I think it was 1.5, 1.5, 1.5. Okay. All right. Awesome. Let's move back to the presentation. That makes sense, guys?
Can I ask a question?
Yes.
Can we use like sine or cosine to figure them out too?
Oh, we're gonna up the game to trigonometry.
Sorry.
Okay.
Just
Yes.
Asking for a friend, not for me. I'm just kidding.
You can totally use trigonometry to solve this. I didn't want to make things even more complicated, but you can totally use trigonometry. In fact, trigonometry, though sine, cosine, that stuff is probably the better way to do this. Okay, because what we showed you here only works for the special right triangles. So since you're bringing it up, and who's this, by the way?
Tiffany.
Tiffany. Since you're bringing it up, let's talk about that. Okay, so let's go back to the whiteboard. Why not? I always like to have fun challenges.
I didn't remember any of this. Any of the ratios. I kind of just went straight to trig.
Okay, fair enough. So let's change it. Rather than a 30, 60, 90, let's make it 20 and a right angle, and then that makes the 70. Okay. And then we know, what do we know? We know this is 2, right? This was 2. And the question is what's, well, we need these two sides. What? Let me not label them. Well, why not? We need these two sides. So Tiffany, did you do it? Like, did you use trig?
I did.
So tell us how you did it.
Oh boy. Okay, so I needed to find the height first, which would be x.
Right.
So I think I did cosine. And you just changed it a little bit for me, but I think I did cosine, and it was, I think, cosine the 20 degrees. Wait, what am I looking at? I don't remember. You changed the triangle.
I'm sorry. I'm sorry. No, I can put it back. Let's put it back. So this is 60 and this is 30. That doesn't matter. We can
It
use
really doesn't.
use the original. No, you're right. Let's put it to the original values so that you can go through your example. So you did, what did you do?
So I think it was cosine 60. And then I think I did that, and it was to find the
What does that
adjacent.
equal?
So that, I don't know.
Oh, all right. Let me help you out. Let me help you out.
It's gonna equal to square root of 3/2.
It's going to equal to
Square root of 3/2.
Well, you're right, but how did you know that?
It's how do I explain this? I remember the things called SOHCAHTOA.
Yeah.
Yeah, there you
Yeah.
go. I was just about to put that out there.
Yes. Yeah. So basically, I had like the cosine 60, and it was like the adjacent over the height. It's wait, I think I mixed
H
up.
is hypotenuse. Oh, let me help you out, Tiffany. I
Yeah,
like this though.
hypotenuse. Sorry. Yeah.
I like this, but I want to go back to who just jumped in. How did you know? Well, to know this, you would have had to know the special right triangle, right? You would have had to know that.
To
So
be
that's,
honest, I memorized all of the angles.
yeah, you just remember, right? But that's why I wanted to say, let's try. Sorry, folks, this is, but you know, let's continue down this path here. I think there's some valuable stuff. Okay, I'm just going to show you with different numbers how you can use trigonometry. So, because it doesn't matter if you use trigonometry, the angle measurements don't matter. Okay, let's make this 10 degrees. That makes this 80, right? Because it has to equal 180. All three angles have to equal 180. So the key is, if we want to get this side, we'll call this side X. Okay, we can use, and this acronym SOHCAHTOA is so valuable. Okay, so if we have 80 degrees, X is the adjacent side to 80. And we know the hypotenuse is 2, right? So we can use adjacent over hypotenuse, right? Adjacent over hypotenuse is X, the unknown, over 2. And if you go to SOHCAHTOA, that means use cosine. So what we do is we say cosine of 80 degrees has to equal the unknown X over 2. Okay, so we can put this in our calculator. Cosine 80. Can someone do that? I don't have, someone have a calculator nearby? Put in 80 and cosine of 80. Anybody got a calculator handy? Or do I have to? I can break mine out if I have to. All right. 0.1736. 0.1736 equals X over 2, right? Solve for X. Just multiply both sides by 2.
0.347.
0.347. So that means, so with this as 2, and this, by the way, this triangle is not drawn to scale, right? 10 degrees is very small. In reality, a 10-degree angle would look more like this, right? Not this. It's not accurate. A 10-degree angle would look more, would look more like that. So this side here is 0.347.
Yeah.
And you can use trig to solve for y, right? We know this angle was 80, so we can use sine, because sine is SOH, sine of is opposite over hypotenuse. So we would just do sine 80 equals y over 2 and solve for y the same way. And it's probably just below 2. It's probably like 1.7, 1.8 or something like that. Okay, so yes, that was a very long-winded way of saying you can use trigonometry. And thank you for bringing that up. It gave me an opportunity to throw in some trigonometry. So that's good. That's good, Tiffany.
No problem. See, I just forgot the easy way.
Well, no, the trigonometry allows you to do this for any type of triangle, not just special right triangles. Okay, great. All right, let's go back to the presentation. So, Ling King, you got us all the way to the explanation, But did you guys all understand? What was your final answer, Lin King?
Yes, I got 20.1. Because after you gonna write down here too. So it's a minus that one 2 square root of 3. It's 1.5 plus 2 times 2 plus 2 times 1.5. So you're saying both ways.
Right.
So it's times 2 after that.
We're going round trip, so she's multiplying the whole thing by 2.
20.1.
20.1. Super. Do you guys, now does everybody understand why Lin King subtracted 2 root 3, subtracted 1.5, and then added back 2 times 2 and 2 times 1.5? Might not be clear. I'll just kind of say she took 8 and she knew she has to get basically this blue distance, and she doesn't want this, right? She wants the blue line from these 2 hash marks and wants to get rid of this from the overall dash distance. So she subtracted out this piece and added in that piece and did the same thing here. She subtracted out this piece, right, which is this, and she added in this whole thing, which is this, okay? And she ended up with like 10.0 something, and when you multiply it by 2, you do get 20.1. Excellent. All right, so that's how we get the distance of our trip. That's a long hike, by the way. 20-mile hike. That's a long hike. Just for those of you who don't hike. If someone says to you, hey, let's go on a hike, it's 20 miles, you probably want to say, you know, it's my first hike. Can we do like 3-4 miles maybe? Right? So just FYI. But let's make believe we're doing a 20-mile hike. And Lin King, if you can just take your pen work off of the screen. And move to challenge 4. It's very important to bring water or hydration on a hike. Very, very important. So the next challenge gave you some a table of how much water is recommended based on 2 criteria: the profile of the hike, easy, moderate, or strenuous, and the temperature forecast for the day. Cold, a little less cold, moderate, and warm, right? Broken out by degrees Fahrenheit. The question is, how many half-liter size bottles should you carry to make sure you have enough water today? Now, this is life and death stuff, right? This is math, but it's like really important math, because you need to make sure that you don't take too little water, which, by the way, I have personally done myself on hikes. And you don't want to take too much because you don't want to carry extra weight unnecessarily. So who can take us through their explanation of this challenge? Who can jump in here? Do we have a volunteer?
Me, Tiffany.
Tiffany, all right, welcome back. Go right ahead.
I'm gonna try. Let's see. So it says we need. Wait, what did it say? So I think based on the table they give us, they say we're doing today's hike would be strenuous. So we're using the hike profile strenuous, and the forecast is a comfortable 60 degrees Fahrenheit.
So which of these rows are we going to focus on?
So we are focusing on the 3rd row.
Right.
Yep.
So what's the important number we need from this height, this table?
So we need the 95.
Right. Boom, right there. Now, you want to make sure you know what that 95 means, right? So you want to say that, use
Cool.
the information, say it to yourself.
So that's the 95 milliliter per mile.
Right.
I believe. Yes. And we are doing 10 miles, 20 miles. Are we doing
20
both
miles.
ways? We're doing
Yeah.
20 mils. So it's going to
Yep.
be was the 95 milliliters times 20. Hold on.
20.1. Not that it changes anything really, but
20.1. So we need 1900 milliliters.
1900 milliliters.
And
Okay.
then we have to go from I went personally from like milliliters to liters.
Okay.
Which was, and I just changed my figures, so I messed up a little bit. I think I got to 3.8. I don't know. I messed up. I just changed my figures and now I'm confused.
Wait, what do you mean you changed your figures? What did you
Well,
change?
I was working it out with 80, not 95 before.
Oh, well, let's just keep it going here because you're doing it right. So you got,
So
you
we
got,
had,
sorry, you got 1,900 milliliters. Can you tell the group how you converted that to liters?
so I multiplied it by,
You divided, by the way.
sorry, I divided, yes, by, crap. I divided by, I don't remember, 500?
How many milliliters are in a liter?
1,000.
Right. So we're dividing by 1,000.
1,000.
There we go. And what do we get when we divide 1,900 by 1,000?
We get 1.9.
Right. Now
And
what
two
what a
colors of
1.9 is 1.9 what? What is that? Again?
liters.
Liters.
And we need
Liters.
half-liter bottles. So we will need 2 half-liter bottles to adequately cover 1.9 liters.
Is it 2 half-liter bottles? Think that through.
Is it 4? 4.
Yeah, but why is it 4? Because 2 half-liter bottles covers
makes 1 liter. Yeah, covers 1 liter, and the 4 will cover the 1.9 which is almost 2.
There you go. Exactly. Exactly. And this exercise was crafted this way purposefully because we need to be able to get comfortable converting from one unit to another unit. Information is not always spoon-fed to us the way we would like it when we get information. Excuse me. And we have to get comfortable being able to move between milliliters, centiliters, liters, half liters, whatever it is, right? So you might have, if I change the exercise, I'm going to put you on the spot, Tiffany, okay? If I change, you know how like those Poland Spring bottles we all drink? How many milliliters? Do you know how many milliliters are in a small Poland Spring bottle? The typical size, the one that you see most often, how many milliliters is that?
I have
185?
Sorry? I heard someone say something.
I think the typical one will be 125 milliliter.
I don't think it's 125. That's a very small amount, but it's understandable why we wouldn't know this off the top of my head. Does anybody know the typical, the one that costs like usually $1 or $1.50 in a bodega?
500 milliliters.
500 milliliters is a little bit big. You can get that. 500 milliliters is like the sport size, I think. So give us another number, lower than 500.
450.
I think it's 250, and I could be wrong, by the way. I don't have this number memorized. I think someone can go and get it if you have a Poland Spring. I don't know why I'm picking Poland Spring. I just happen to, it's a typical brand that we all know. I think the sort of small size, there's also a miniature size, but kind of the small size that you see all over the place is 250 milliliters. All right, so Tiffany, what if we had those 250 milliliter size bottles, not 500? How many 250 milliliter size bottles should we take with us?
We will take 250. Let's say we will take, I'm working this out. 8.
8. Bingo. Exactly. 8. That's a lot, right, guys? you don't want to be carrying 8 bottles on a hike, but it's a long hike. What can I tell you? But that's great. Thank you, Tiffany. That was very good. So yes, the answer is 4 500 milliliter bottles of water. Great. All right, we got 2 more challenges for today. Challenge 5 is using a functions. Okay, got to get comfortable being able to read functions and working with them. Oh, and it involves a graph too, even more fun. So you want to figure out like how many, you want to kind of estimate or project how many calories you're going to burn on the hike, right? So of course you can get the calories later, but you want to know up front, you want to get a good projection or prediction of that. So you read that someone created a function to help estimate calories burned as a linear function of hiking distance traveled. Okay, so in this case, x, the variable x, is the hiking distance traveled in miles, and then f of x, right, or the function or the outcome, once we sort of do the math using the other numbers, the 110, the 140, right, out pops the estimate of calories. Okay, so this function gives us an estimate of calories where our input is the number of miles hiked. So part A, we know that we're hiking 20.1 miles. So how many calories does this function suggest we're going to burn, rounded to the nearest calorie? Anybody have an answer for that one? Should I call on somebody?
2,910.
That's Tiffany again? I think I recognize your voice, I think.
That was me.
Okay, so Tiffany got 2,910. And by the way, based on what exact value of x you use here, if you use the rounded answer or the not rounded answer?
I had 20.
20. Okay, so you use 20. So basically, just talk it through. Let's make believe it's 20. What are you actually doing here to get that 2,910?
So I plugged the value of 20, which is the distance traveled, into x. So yeah, right there. So it was 140 times 20 plus 110.
Right? Perfect. So we know our order of operations. We do this multiplication first, and then we add 110, and then that result is in fact the result of the function, and it is about 29 something, depending on what exact value you put in there. I think if you use 20.1, you get 2940, but that's not a big deal. You got a good estimate. Now, how about the graph, Tiffany?
I did not do that at all.
Okay. Did anybody do the graph? Anybody do the graph? Sergey, 2924. Okay. That sounds about right. Sergey, did you do the graph by any chance?
No, I'm actually just thinking about it and trying to figure out if we, for example, taking the x as 0, so we have a point on the x, axis, y-axis.
Oh, sorry. I didn't want to show you, but okay. I'm
It
gonna
would-
just
for
I'm
me
just
to-
gonna
yeah.
share the graph here. Why don't you talk it through, Sergey? Talk through this graph.
So, for example, to start, I need to find the intersection, and where is x, I'm taking 0, and it gives me the intersection with the y-axis at point 110.
Perfect. We call that the y-intercept.
Y-intercept, yeah. And so then we know that we hiked 20.1 miles. and it gives me exactly 2,924 miles. on
So
that
that,
value.
so that gives you 2 points to plot, right? Gives you 2 points to plot. And then you can just simply draw a line between them. And that would be the visual representation of this function. This red line represents this function. If you put another value of x in here, between 0 and 20, you will see that it should end up on this line. So to prove it to you, if we have x is 5 miles, and someone do 140 times 5, please, and then add 110 to it, and then tell me what that is.
810.
Doesn't sound right. 5 times 140,
It's 700.
700. Okay. And we would go up at 5 miles, and look at that. 700 is about, looks like about perfect, right? So any point on this line, if we take the coordinate of that point, the coordinates, let's say this one, this is 15 for the x value approximately, and looks like about 2250 or so for the y value approximately, right?
Yeah.
That's the beauty of data visualization. When we take functions and plot them, it allows us to visualize what the relationships look like for any given, in this case, independent value is the miles, and the dependent variable is the calories coming out, okay? And it allows you to see that across the board. And this is called a linear function. Why? Because there's x is to the first power. The variable is to the first power. If I have a function like this, f of x equals x squared plus 10, that's not a linear function. That is a quadratic function, and it would it wouldn't be a straight line. It would be more of a curved type line. Okay, just as an example. It can be also x to the third, x to the 10th. Doesn't matter. Okay, all of these are called are quadratic or polynomials, and then linear functions, which is what we see mostly, unless you're a data scientist, are to the first power. Okay, any questions on that? Makes sense, right? So it's really important. It's a really good skill. The reason why these exercises are here, most of them, all of them, for a reason. Okay, because we believe that each of these help build skills around certain mathematical principles that are commonly used. Right. So every week you're going to see now we're going to repeat the same theory using different practical applications. Okay, so you're going to see this repeated again in the future. All right, I think maybe there's a question in the chat box. Let me just check real quick. Oh no, it's wrong link, posted a link to a calculator. All right, challenge number 6. Now, I must say that we, by the way, these exercises are literally being created from scratch every week. We're not pulling these from some website and then just giving them to you. So unfortunately, though, the reality is that sometimes we make unintended mistakes, right? Or maybe the wording is not clear, or there might even be a mistake at some point. So of course, we're doing our best to quality control, but frankly, challenge number 6 had some problems with the way it was originally worded for you. We went ahead and resent you guys a new PDF with a different exercise until we realized that even then part B was a little bit unclear, and could have been could have been interpreted a couple of different ways. So the wording here is a little bit different than what we sent out a couple of days ago. Let's give it a shot, okay? So you're hoping on this hike that you'll get to see some deer. You found some information that breaks down the hike into 2 segments and gives you the probability of a deer sighting in either section, okay? So the probability of seeing a deer in the first section is 10%, and the probability of seeing a deer in the second section is 20%. Part A, what is the probability you'll spot a deer in section 1 and also, underlined, in section 2? Now assume you pass through each of these 2 sections only once. In other words, forget about the whole round trip aspect, okay? You're passing through section 1 and section 2. You have probabilities of seeing a deer in either section. What is the probability of seeing a deer in both section 1 and 2? Can anybody help us with that? Can we get someone other than Tiffany, who's been great? Okay. Anybody else want to jump in here? And Sergey just answered. Xiao Ting, we haven't heard from you today. Can I call on you?
Because since when I look at the problem, there was a mistake. So I didn't do question 6.
Oh, fair enough. But now that you see this in front of you, maybe you are able to just do it on the fly.
I'm not sure I can do it or not.
Okay, fair enough. Did you learn probability at all yet?
Still learning.
Okay, fair enough. So who's learned? That's fine. So who's learned probability? Who can help us through here? Yanmin. Yanmin, your answer is correct, by the way. So Yanmin, you want to unmute and talk us through part A? That's the answer for part B.
Part A for the section 1, the possibility is 10%. Then for the section 2, the possibility is 20%.
Yep. So what would be the answer to part A? The probability you'll see a deer in section 1 and in section 2.
I think that will be 10% times 20%.
Well, first of all, you're right. But let me ask you a question. Let's just forget the math for a second. Do you, if you know the probability of seeing a deer is 10% in one part and 20% in another part, do you think the probability of seeing it happening twice, seeing a deer in both first part and the second part, is it going to be like a very low number or a very high number?
Low, very low number.
Correct. So let's say you thought maybe you add that, you don't know probability and you thought, well, maybe I add 10 and 20, right? And we get 30. Why would 30% be wrong? You don't have to explain it mathematically. Why does it feel wrong? Does 30% feel wrong?
Yeah.
Feels wrong.
Yes, because that possibility should be lower either for section 1 or section 2.
Right, exactly. This is wrong, people, okay? When we do probability, and this is called, for those of you who are just learning probability, or maybe you learned it real quickly and haven't really spent more time with it, this is a compound situation, right? Meaning there's, multiple events have to happen. So as we just said, it's not going to be a higher probability for something to happen both for one thing to happen and another thing to happen, both of them having whatever their probability is. Having them both happen is all going to be a lower probability than either one of them independently, not higher. It's not going to be 30%, okay? So for it to happen here and there, the operation is multiplication, right? So that was the correct intuition. It's, of course, with decimals, though, not 10. 0.1 and 0.2 multiplied together, and that gives you 2%, 0.02. 0.02, which is 2%, right? To go from decimal to percent, we just move decimal point 2 places and then tack on the lovely percent sign. Okay, so this, and folks, little bit of learning for you. In probability, for the most part, when you see the word and, that's a compound event. Compound event means multiply. Okay? Please remember that. General rule, this and that have to happen. You are going to be multiplying these various probabilities. Sometimes they'll be written as a percent. Sometimes they'll be written as a fraction. Doesn't matter. Doesn't matter. Right? 20% is 1 over 5, 10% is 1 over 10. Either way, when you see and, you're generally multiplying. Don't get caught up and think you add. Okay? Now, and by the way, if this is new for you, that's wonderful. Glad you're here. We will be doing more probability exercises in the future, different from different perspectives. So you're going to have a chance to keep working on this if you come to the Tuesday meetings. All right, part B. And Ron Ling, you got this one correct. So I'm very excited to hear how you did this. So the question, what is the probability you'll spot a deer in at least one of the 2 sections of the hike? Okay. That's a bit tougher than part A. How did you do it?
Wait, I think you say Yang Min, right?
Oh, it wasn't Ron Ling who was speaking. I'm sorry.
I'm not speaking. I'm listening.
I'm sorry. I'm sorry. That was Yan Min. Sorry.
Yes, yes, I'm Yami.
Yan Min, go ahead and please tell us how you got your answer.
So I think there are 3 parts for part 2. The first part is the possibility you see a deer in session 1, but I don't see a deer in session 2. So for that part is 10% times 80%.
So this would be the probability of, I'm going to call this, we're going to refer to this as A and this as B, okay? This is probability, this is basically probability that you see a deer here and don't see a deer here. We'll call this, the squiggly line means not B, okay?
Yeah.
Okay, keep going.
Then the second part is I see a deer in session 2, but I don't see a deer in session 1. So that will be 90% times 20%.
So this is probability of not seeing a deer in section A or in the first section and seeing a deer in the second part. Okay, so here's 2 situations. Okay.
And the last part is I can see a deer in session, both in session 1 and session 2. So that will be 10% times 20%.
Awesome.
And add them together.
Awesome. So in this case, and this is going to be a little bit hard if probability is new to you. It's going to be hard. You might be saying, hey, he just said don't add. right? So why are we adding now? This is a little bit of a situation, and the solution here is a little bit tricky question. Okay, so the wording says the question you have to ask yourself is, how many different scenarios can we have at least one sighting in the two sections? At least one sighting means we cite in A, we don't cite in B, or we cite in B and don't cite in A, or we cite both in A and B. Those are three distinct situations, and we're adding them together because you notice I said the word or. And in probability, when we say or, we normally mean add. So we're usually adding when we say the word or. And again, like I said, when we say the word and, we're generally multiplying. Okay, so if you guys check this math and you just put this into your calculator, you will get 0.28. So that was very good. Now, let's just continue on this for a second, okay? Because there's a couple of other ways to look at this exercise. There's one other way I really want you guys to see. Does anybody know another way you can attack
Yes,
this?
I also know the second way to calculate this possibility.
Okay.
Because the question is to ask the possibility to see a deer at least one of these two sections. So the opposite of this possibility is you don't see any deer either in section 1 or section 2.
Perfect. At least one, I'm going to write this down, people, is the same as 1 minus never. Okay, a lot of times, on a lot of exams, you'll see this at least once, like at least once. So actually the easiest and fastest way to deal with at least once, because at least once, as we pointed out above, actually can happen in 3 different ways. But at least one is the same as 1 minus never, meaning never having a deer sighting, never having a deer sighting. And just continue the math now. How do we calculate 1 minus never?
So that will be 1 minus 90% times 80%.
Very good, right? 1 minus I'm going to just put it in decimal form. 1 minus essentially, if you take these probabilities and you convert them to 100 minus them, that's the probability of it not happening. Okay, right? So you can write that as 90%, or you can write that as 0.9, right? Whichever way you want to write it. You can write it as a fraction. It doesn't matter. Okay, so I'll just keep it as a decimal. 1 minus not seeing a deer in first section, 0.9, and means multiply, not seeing a deer in second section, 0.8. This is 0.72. 1 minus 0.72, 1 minus 0.72, come on, equals 0.28, which equals 28%. Excellent. So that's a little example as to how we might use probability in a real life scenario, right? So 28%. So you see the probability of seeing a deer in both parts is very low, right? It was like 2%. And the probability of seeing a deer at least once is a little more complicated and obviously has a higher percentage because you can see the deer in the first part, the second part, or in both parts. Okay. Woo, that was tough. Well, what do you think, guys? Let's just take a minute here and reflect on all this. We got 4 minutes till the end of the meeting. I'd like to hear from a couple of y'all who've been on the call and have been a little more silent. What do you think? What's your reaction to all this? Elliot, you have your hand up. I'm not sure if that was from before, but since your hand is up, Elliot, I'm going to ask you, what's your what's your thought on all this math?
Well, my hand was up from before. I didn't realize it didn't
that's
go down
fine.
its own. But my thought on math overall, I mean, it's fine. I think stuff like, I mean, the math itself, the implications you used are ideally real life implications in terms of like, if you go hiking or, probability and such like that. So I think it's pretty helpful. I mean, I personally like probability stuff better.
Yeah, no, for sure. But I mean, like, just was it understandable? Was today understandable
Oh
for
yeah,
you?
yeah. It was yeah.
Okay.
A lot of it was just to be honest, like kind of like a refresher. Like I haven't done this type of like math in a while. Most like I haven't done this type of math in a while. So it just a lot of times it's just kind of like you just need a refresher.
Right. Of course. Well, that's exactly it. That's why we're doing this. Thank you. Anybody else? Anybody want to share their thoughts? How was this for you? Just share you whatever you're thinking. It was tough. It was not that bad.
The question is kind of interesting because all the questions are related, unlike the questions from last time. It was the question from last time was not related at all. So for me personally, I want to see more of these kind of questions. All the questions are gonna be related.
Yeah, absolutely. Well, they will be. They will be. So I'm glad for that feedback. Give us feedback, people. This is new. The MathMinds project is a new thing. Give us feedback. Tell us what you like, what you don't like. We're open. So this is for you guys. This is not this is not meant to just be forced to you. Any other thoughts, reflections on today? How about
yeah,
from? Oh, go ahead. Who's this?
me rolling.
Oh, Roland. Go ahead.
Yeah, I think the challenges number 4 actually confused me before you're going over.
Okay. Which was 4? The one with the water bottles? I can't remember.
Because I didn't realize that you had to convert the units.
Right. And you know what? In real life, you often have to convert the units, right? Because you don't get the information presented to you the way you want it, right? Or the bottle size can be something different. What if, can like Tiffany did a good job. I threw her a little curveball there, changed it to 250 milliliters. You got to be able to kind of roll with the punches that way, right? And kind of building your comfort level with numbers helps you quickly do that. So thank you. How about from the math mentors? What do you guys have to say? Or from Michelle or Illy, Lane King?
I think overall it was, it's challenging. It's not easy, but it's kind of just like a muscle that I need to practice using. And I would just say also that the one that had to use trigonometry definitely had me confused, and I'm really excited to go back and review my geometry.
Yeah. No, listen, I would never, I do this for like I do this math stuff all the time. Like I help folks with like ACT prep. So even trigonometry, you don't use too often. So I've had to myself review the trigonometry stuff. So it's understandable for us not to remember that if we don't use it. So fair enough. Okay. Anybody else?
I think it's
Yes.
going.
Okay, go ahead.
Sorry.
Yeah, I think like it's quite rare. Like I'm doing calculus and then back to algebra and geometry. Like, would it be better? We will have like calculus in the future.
You want us to add calculus to this, Lin King? Is that what you want?
Yes, yes.
Oh, goodness. Please don't get me started. We'll be doing integrals, integral mathematics. I think we'll stay away from that. Only because in the business world, you rarely use calculus. So we're going to stay away from calculus. But listen, Lin King, if you have any questions about your calculus, please, I can try my best to help you. Okay. So feel free.
Thank you.
Anybody else? Well,
Wait, I have one question.
yes, go ahead.
Are we going to have finance problems and math problems in the future?
Oh my goodness, you are a perfect segue to our last thing here, okay? Because, oh, I thought I had a slide on this. I don't have a slide on this, but I will tell you that our next math mission, in fact, our next 2 math missions are going to be finance-oriented math missions. So I'm super excited, okay? So now we're really gonna get into stuff you guys deal with every day. So we have for you, for next Tuesday, math mission called Show Me the Money. And so these are all questions revolving around personal finance decisions, okay? And then the following week, we'll put together a kind of part 2 that will be a little bit more business or corporate finance related. Okay, so special for you and for anybody else who wants to join. Yes, we're doing finance, and then to give you a head, one more week after that, we'll devote one of our sessions to Excel skills or building it. The challenge will be an Excel challenge. Okay. So we're going to have 2 finance challenges followed by an Excel challenge. And that's what's coming next few weeks. Okay. Thank you for the question. Anybody else have a question or a comment?
I like the way you show when at what points the math the math that you're showing is useful in people's lives. I really appreciate that. And it would be great to see when it's used in operations management versus like in finance but you've done that already and I appreciate that. So thank you.
Yeah, no, sure. Thank you for the comment. And when I hadn't thought about it, but I might do actually what kind of got me even thinking about this whole MathMinds project is from teaching operations management. When I saw how the math was underpinning many of the theory and folks were struggling with the math. So maybe we can do an operations oriented mission. We can surely do that. So we'll do a finance oriented missions, and then sure we can do an operations oriented mission. Why not? So that's a good comment. All right, so it's 7:34, so we've already kept you over. Guys and gals and everybody, help us by spreading the word for this project, okay? Especially Elliot, you're here from Baruch, and we're happy to have you. And we have recently connected with.
I'm not here from Baruch, Professor.
Sorry.
About last semester, 2 semesters.
Oh, right. I'm confusing people. You were a Brooklyn, my student. I'm so sorry. I'm so sorry. Actually, from Baruch, I think the gentleman who was here from Baruch is already dropped off. Nevertheless, we want to continue getting our fellow students at Brooklyn College in on the project. So please help us by, we're doing this, we're not on campus, we can't put flyers in Kopelman, in classrooms. So please help us by sharing our promotional flyer and registration link. And Michelle, can you actually see if you can post the flyer in the chat box? I think you can put a file in there, and also the registration link. And folks, help us bring a friend to next week's class or next week's training, I should say. Help us increase the size here. I would love to have 100 students joining us on Tuesdays. So help us with that. Take out 5 minutes and just help us. Appreciate that. And also, if y'all have any questions about math theory or anything, frankly, related to math, it could be related to your classes right now. It can be related to any of these kind of more basic topics. And you want more, if you have a question or you want like more resources, you know, I have this thought to like build recorded videos on different topics. I just haven't gotten to it. But if you want more exercises, you want to do more exercises, please email me. I'll be happy to help you with that. Or if you have a question about your math in your course, if it's something I know, I'll be happy to help you. Okay, just email me at I'm either at ken.globerman@brooklyn.cuny.edu or at ken@brooklynnobrainer.com. Either way. Okay. So on that note, I think we're gonna end the meeting for the day. If you have any, unless anybody has any other final questions or comments.
Hey, I just wanted to say I will be emailing you all the flyer and link. I just wasn't able to pull it up to put it in the chat, so I'll be emailing all of you that tomorrow.
Fair enough. Thank you, Michelle.
Thank you.
All right. All right. Unless there's another question or comment, we're going to end the meeting for the day. Wish you guys a wonderful rest of the week and looking forward to seeing you. The next mission is going to be out tomorrow, and work on it and come to our meeting on Tuesday. Get ready to talk about personal finance. See you then and have a great evening. Take care, everybody. Bye-bye.